Hello, everyone, and welcome to Death and Destruction, Part 2 Earthquakes. Earthquakes really are among our worst natural disasters. I mean, I'm joking, but they really are. They strike utterly without warning. We can talk about more or less earthquake prone areas, but there's really no way to predict them. There really isn't. And so they tend to, there's an earthquake happening when it happens. It's not like a hurricane where you can see it coming, days ahead. There it is. And so, engineering is a big deal. How well built is your building? Preparedness is a big deal, and all this kind of stuff. So, I mean, like I said, we can talk about more or less earthquake-prone areas. Certainly, you're at more risk in, say, Southern California than you are in Florida. But no one can predict when an earthquake is going to happen. If they tell you they can, they're probably trying to sell you something. So anyway, so let's take a look. So earthquakes what happens where you have portions of the Earth's crust sliding past itself, and these breaks in the Earth's crust are called faults. And as we'll see here in a minute, there's four different kinds of faults that we can place into two different categories. But first, let me just say this because this is kind of important. Although it's not on the review sheet, so how important could it possibly be, right? But no, if an earthquake, let's say, lasts a minute, this isn't like, you know, the earth is grinding along for a minute. And I usually do this with my hands in front of you guys, but I can't do that. So here we go. So what happens though is pressure builds. I'm going to grab my fancy little pointer thinger here. Pressure builds, and the rock will initially bend um, along the fault. And then it will get to a point where it can no longer support that bending, and then the rock will break and almost literally bounce back and forth. That's the earthquake. The bending and the breaking, the bending happens over time. The breaking and sliding, though, happens very quickly within like a second or two. But the waves that result from that travel outward. And that's what we feel when we feel an earthquake. This is called the elastic rebound effect, by the way. And the nerdy geologist in me is compelled to point out that they are actually using the word strain the wrong way here. That's not strain, it's stress, but whatever. Anyway, they kind of liken it to breaking a stick, which works pretty well. You bend a stick, and then, at the moment it breaks, that's when you feel the vibrations running through the stick, right? That's the earthquake right there. And then afterwards, we kind of establish a new equilibrium. Okay, so yeah, and so rock actually does bounce back and forth under these conditions. Now, let me also say, though, these conditions are usually pretty far under the ground. Earthquakes don't usually happen at the ground surface. There will be fault traces that breach the ground, but the earthquake itself is usually happening pretty far down, at least a mile or two down. So, okay, so there, as I said, there are four kinds of faults that we can put in two categories. I figured out how to make my PowerPoint screen take up the whole wide screen and not just a little square, so I'm pretty happy with myself. So anyway, there's four kinds of fault that we can put in two different categories. There are strike slip faults and there are dip slip faults. Okay, strike slip faults are kind of like the San Andreas fault, right? This is what's happening when you have portions of the Earth's crust moving past each other, right? This is kind of the equivalent of a transform plate boundary, okay? And in fact, transform plate boundaries make strike slip faults, okay? And so there's two kinds, right lateral and left lateral. And the way you tell the difference is you ask yourself, okay, if I'm standing on one side of the fault, so let's say I'm standing here, and I look across the fault. So I've got a fault running through here. I've got a little lame little looking river thingy here, cut by the fault and displaced by the fault. And so I ask myself, if I'm standing here and I look across the fault, what direction do I need to look to see the feature, right? And if I'm standing here and I'm looking this way, I have to look to my right, okay? Right lateral. Now, it doesn't matter what side of the fault you're standing on, right? If I'm standing over here looking this way, imagine yourself a little ant standing on your computer screen looking this way. You're still looking to your right to pick up the fault. And this is where I would do a little thing with my hands where I would turn them around and show you, but I can't do that. Okay. But it doesn't, it's not like it's a right lateral this way and a left lateral that way. No, 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 no. Imagine you're standing on one side of the fault, looking across it. What direction is that other block moving? It's moving to the right. If I'm standing over here and I look across the fault, that block is still moving to the right. Okay. The opposite of right lateral is left lateral. So if I'm standing over here and I look across the block, it's moved to the left. Okay. If I'm standing over here and I look across the block, it's still moved to the left. You turned around, right? So left is the other way. Okay, so right lateral is always right lateral. It doesn't matter what side you're standing on. Left lateral is always left lateral. It doesn't matter what side you're standing on. Okay, both of these are very common at transform boundaries, right? The San Andreas fault is a great big right lateral strike slip fault. Okay, and so, if you're standing here, you're on, like, let's say, the North American tectonic plate. You're staring at the beach. The beach is moving to the right, right? If you're in California, you're staring to the west, and the beach is moving to the north. That's right lateral. Okay. So in the field, here's what they look like, right? And so let me try a fancier thing here. Hold on, guys. Let's see if I can do this. Let's use the pin. Ooh ah, right? And so here's a coal bed here, right? I can't draw straight, don't mind that. There's a coal bed there, right? Here's a fault running across it like this, right? And so if I'm a little ant walking along my coal bed, I have to turn to my right to pick up that fault again, to pick up that coal bed again, right? So this fault here in the middle has displaced this rock to the right, as I look at it, as I stand on one side and look to another, right? So if I'm standing here, see, I'm liking this little thing now. If I'm standing here and I'm looking this way, right, I have to look to my right to pick up that coal bed, right? It's the same way if I'm standing on the other side of the fault. I know y'all are sick of me drawing on the slide already. But if I'm standing here, right, and I'm looking this way, I can't draw straight lines. I still have to look to my right to pick up the fault. I know that arrow just went to the left, but imagine you're standing here looking this way, right? It goes off to the right, okay? And so let's take a look at a few more. And I want to get rid of all that. And so let's take a look at this. Right here's a road in California. Roads are good because they're straight and you can see easily, right? And so although the picture's kind of grainy, you get the idea, right? There's the fault right through there, right? And so as I stand here and I look across it, this is moved this way, right? It's moved to the right. As I stand here and look this way, this is moved this way, okay? But once again, if I'm standing over here, move to the right lateral, okay? Wish there was a hotkey I could push to get rid of that ink. I'm sure there is. Okay, so here's another one I won't draw on it because I already drew on this one. This was an earthquake from actually just I don't know, about a year ago now, out in Southern California. Some friends of mine went out to find the fault trace, and sure enough, they did. And sorry, they marked either side of the fault with beer bottles because geology. But anyway, sorry, needed some coffee there. So anyway, so this fault trace is a little more difficult to see than the other ones we've been dealing with. It runs right about through there. Kind of there. But I can't draw. But anyway, especially not with a little pen on a PowerPoint slide. But anyway, as I look across this, right, once again, displacement is to the right, right? And so here I'll draw a whole arrow. Ooh, look at that, fancy. So displacement is to the right, right? And here I did I don't know if it's the same picture or not. It doesn't quite look like it. But here I drew in the fault and then drew in the offset, right? So as I look across it, it's off to the right. Okay, so here's even when you set up the fancy laser range finding gear, which is what they're about to do here, you can pretty distinctly see this berm here Let me go back to my pointer because I'm tired of drawing on slides. You can pretty distinctly see this berm here offset to the right as it goes across. And like I said, eventually they'll put some laser rangefinders up on these stands to track any aseismic creep or any other movement or anything else that's going on along this fault line. So yeah. So here they also had a drone. There's that same area photograph taken from the air. You can see how the road has been displaced to the right as you go across the fault. This is left lateral, right? So here I got a fault running right through here. My pictures are grainy. This is annoying. I don't know why. But anyway, I got a fault running right through here. I've got a nice quartz seam running across the fault. It picks up to the left as we go across the fault. Right here's a farmer's field. Fields are great for this too because it's very clear what's going on. And so there's a row, stops at the fault, off to the left, picks back up. Right, left lateral. Um, Okay, so both right and left lateral are very common at transform boundaries. The San Andreas fault produces a lot of right lateral earthquakes. Puerto Rico fault produces a lot of left lateral earthquakes. The East Anatolian, I think, is also left lateral, but very common at transform plate boundaries. Um, at sorry, at convergent and divergent plate boundaries, we get what are called dip slip faults. Dip slip faults, we need to view these from the side, right? When we were looking at strike slip faults, we were looking at them from above. Now we need to look at them from the side. There's two kinds, normal and reverse. Okay, so let's take a look. So normal, if I look at it from the side, so here's the fault. I've got two blocks. I've got this block and I've got that block, right? The block above the fault is called the hanging wall or the head wall. Let's call it the head wall. The block below it is called the foot wall. Okay, and so what you do is you ask yourself, okay, um, did the hanging wall move up or down relative to the foot wall? So I drew a little feature here that goes across the fault and it's been dropped down, right? This feature, I know I can't help myself. This feature here, this blue bed, whatever it is, should be up here, but it's not, right? It's been dropped down. Man, that's even a worse error. Oh, that's good. That's not so bad. Oh, there we go. Cool. It's been dropped down. Okay, and so yeah, so we call that normal. Normal faults are very common at divergent plate boundaries because at a normal fault, if you pull this rock this way and you pull that rock that way, what's going to happen is pretend that's an arrow. But if you pull these, what's going to happen is this head wall is going to tend to slide down. Right. On the other hand, over here, for example, if I push on this block and I push on this block, now that head wall is going to tend to slide up. Okay, and so this normal faulting is very common at divergent plate boundaries. Remember when we were talking about mid-ocean ridges and I said, look guys, ridge push, not such a thing, right? I mean, it's a thing, but it's not a huge thing because the faulting is wrong. We know this rock isn't being pushed on. The way we know the rock isn't being pushed on is because mid-ocean ridges are normal faulted. Normal fault, normal fault, normal fault, one after the other, after the other, after the other. Okay, so we know that it's being pulled on because normal faulting, if I pull on this block, let me go back to the pointer. If I pull, there we go, nope, yeah, if I pull on this block and I pull on that block, this will slide down, right? So normal faulting. Let me see. This is one of those cases where, okay, so here's a normal fault in the field, right? Here's the fault running right through here. We have a bunch of interbedded sands and muds. This should come across here, but it's been dropped down, right? This is the head wall here, right? It's moved down relative to the foot wall, okay? Here's two normal faults, right? There's a normal fault right here. Let me draw. I know. I like it though. Okay, there's a normal fault right here, running right down through there like that. And then there's another normal fault right here, running right down through there like that, right? This one is bigger, okay? You can see the offset here, is, like that, right? Where the offset here is, it's just like a foot up there, right? It's not very much at all, right? And so, And so yeah, so once again, this is the hanging wall for this fault here. This is the hang. Let me go back to my pointer. Sorry, guys. Here we go. I know I'm having too much fun with this. This is going a little crazy. Okay, now for this fault right here, this is the head wall. This is the foot wall. Head wall is slid down, right? For this fault here, this is the head wall. That's the foot wall. Head wall is slid down, right? Both of these are normal faults, okay? And that's the way that kind of works. You end up getting a lot of, a lot of the same kind of faulting in an area. You won't often get, a normal fault here and a reverse fault there. That doesn't really happen, right? Here's a couple normal faults. Now you can see we got a wedge here. Okay, so we've got two faults. I've got one obviously over here, and I've got another one over here. Okay, so we got two faults. Both of them are normal. Okay, this wedge here, this is the hanging wall. I'm gonna try drawing H. Let's see how I do. Ooh, so far so good. Ooh, ooh, ooh. Oh, cool. This is the hanging wall for both this fault and this fault, right? This is underneath the fault. We're going to try to draw F for footwall. Ooh, not bad. Ooh, doing pretty good. Okay. And then this is a footwall over here, right? And so, well, that was not so good. That's okay. Okay. So for both of these faults, right? This is the hanging wall, then that's the footwall, that's the footwall. So ask yourself, did the hanging wall move up or down relative to the footwall? Well, for both of them, it moved down, right? If I just trace this bed right here, right, this bed should be up here. It moved down, right? My little lousy arrow. This bed should be up here, right? It's down here, right? It moved down, okay? So in both, why am I little loopy little arrows there, but that's okay. So anyway, so you get, hopefully you get the idea, right? I have two faults. They're pointed in different directions, but they're both normal faults. Let me get rid of all my silliness. They're both normal faults, right? This is a head wall for both of these faults, and it's moved down. These wedges sliding down are not at all unusual. Sometimes they are literally miles across. This one's only a few feet, but sometimes they are much bigger than that. But both normal faults. Here's a reverse fault. Right here we're in China, right? And so you can see the fault running right through there more. Or oh, I hit my computer. Hold on, let me try that again. I'm having too much fun here, guys. Okay, so let's try it without hitting the computer. Okay, so here's the fault running right down through there, right? And so you can see, here's the head. This is the head wall here, right? It's above the fault. Here's the foot wall here. It's below the fault. Okay, and so the head wall now, you can see this layer here is a really nice marker layer with a lot of soft sediment deformation, right? And so you can see how when it went across the fault, it got shoved up, right? This has been moved up. So arrow. There we go, arrow. Okay, and so this has been shoved up. Okay, so this is a reverse fault. Okay, the rock on top of the fault has moved up as opposed to down. Right, here's another reverse fault where I had the foresight to actually do it this way, and so you can see. Let me see. Do I have the other rock? Yeah, I do. Okay, so you can see here's the fault running right up through here. And then here, the block above the fault has been shoved upward. The block below it, relatively speaking, is moved downward. Okay, and so reverse fault. Reverse faults are very common at convergent plate boundaries, right? In fact, this is in China. Sorry, let me go back to the previous slide. That's in China, right? And so, it's not all, it won't work every single time, but you remember that India is hitting China. That's a convergent plate boundary, right? And so, if someone puts a gun to your head and says, I'm standing on a fault in China, tell me what kind of fault it is, guess reverse, okay? You might not be right, but you probably will be. There's going to be a lot of convergent boundary around there. And so, yeah, so another reverse fault there. Now, let me go back 1 second here. These drawings like this, that I was showing you, those are in the those are in sorry Those are in my courses. You have one sheet called fault drawings, I believe, in the root directory in the geology module. So you have those drawings, okay? I'm going to probably put one of each on the test, right? I'll give you one dip slip and one strike slip and ask you, okay, what kind of fault is this? What kind of fault is that? Okay. I'm not inclined to put photographs on the test because those kind of freak people out a little bit. If I do, I'll probably draw arrows on it or something, but just be able to recognize a right lateral, left lateral, or a normal or a reverse fault. Okay. Alrighty. All right, so let's go back here, there. Okay, so if we ask ourselves, where did the earthquake happen? There's two different words that we use: focus and epicenter. Coffee's good. Focus and epicenter. So focus is okay. Here's the thing we want to get: earthquakes don't happen at the surface. They might breach the fault might breach the surface and move, but the actual locking up and slipping is happening underground, usually at least a mile, really usually 2 miles underground, right? That point underground where the earth, the rock actually, locks up, pressure builds, and the rock breaks and slides. That point underground is called the focus. Now, when we talk about where an earthquake is, and I don't understand the grainy pictures, but anyway, I need to get over it. When we talk about where an earthquake is, we don't usually talk about the focus. We talk about the epicenter. Epicenter is a word that is, sorely abused all the time, especially lately. We like to talk about the epicenter of the outbreak, or the epicenter of this, or the epicenter of that. Technically, that's probably not the best word to use, but we do it anyway, and that's fine. The Greek prefix epi, though, means on top of. It doesn't mean the very, very center of everything. It means on top of. And so the epicenter is that point on top of, let me get back to my laser pointer, not my little silly little pin, is that point on top of where the earthquake happened. So when you talk about where an earthquake is, yeah, the epicenter is as close as you can get to it without digging a hole. And that's going to be the center of destruction and whatnot. But that's not actually where the earthquake happened. The earthquake happened underground. So there's two words: focus, which is that area along the fault underground where the slippage actually happened, and then the epicenter is that point on the ground surface above the focus. Alrighty, so once an earthquake happens, so rumble, rumble, rumble. Okay, so the rock had pressure applied to it, it bent, and then it broke, and when it broke, it released all these waves, right? It's kind of like throwing a rock into a swimming pool, right? The rock hits the water right away and goes down, but the waves, as a result of that event, can last for as long as they last. And so when we think about earthquake waves, there's two different kinds: surface waves and body waves. Surface waves travel along, oddly enough, the surface of the Earth. These are kind of similar to waves in water. Body waves, on the other hand, travel within the Earth. Okay, now, surface waves actually do the most damage, but we are going to concern ourselves more with body waves, actually. Because body waves, as I said, travel inside of the Earth, and they can tell us something about the inside of the Earth. So there's two kinds: P waves and S waves. P waves travel by compressing material, right? They travel by compressing rock, right? Here is one P wave at a time going down a block of rock, right? And so, boom, there's a P wave traveling down that rock. Okay, P waves travel faster than S waves, which will be our other kind of wave. They also travel through solid or liquid rock. S waves will not travel through liquid rock. And so, if you're recording an earthquake and you only get P waves, you're going to be, you don't get any S waves. There's some molten rock somewhere between you and that earthquake. And so, as we'll see here in a moment, that's a very valuable tool. So there's what a P wave looks like. Here's what an individual S wave looks like, right? Now the rock is moving up and down, right? Back in the bad old days when we used to teach this stuff with slinkies, right? I would draw a slinky out, and then I would, kind of hit one end of it. and that would send a P wave down the slinky. If I draw the slinky out and I shake it up and down, that sends an S wave down through it. And of course, earthquakes, do both kind of at the same time. Now remember, P waves travel faster, S waves travel slower. Surface waves actually travel slower than both. I can show you some surface waves. This is a love wave. Now, I know it kind of looks like the rock is moving up and down, but it's moving back and forth. Look at the end, back and forth, right? And so this is one of two different kinds of surface waves, love wave. And then the other kind of surface wave is a Rayleigh wave, where the rock moves basically in a circle. It moves a lot like water in the ocean, only it's going the wrong way. But anyway, it moves in a circle, and so these are the ones that do the damage. But they travel more slowly, right? P waves, on the other hand, are the fastest of them all. So, no, you cannot predict an earthquake, but you can build a warning system, right? If you are far enough away from that epicenter, there might be enough time between the time that first P wave hits and the time those surface waves hit. And so that's kind of what they're working on now out in California is, a warning system based on those P waves. I mean, you might only have a few seconds, but it might only take you a few seconds to get to a safer place. And so, yeah, so no, they can't predict earthquakes, but we are working on warning systems for them, especially now in this age of cell phones. You can get word to everyone pretty quickly, the second there's an earthquake. So P waves travel faster, and P waves will travel through solid or liquid rock. S waves, shown here, travel more slowly, and they will not travel through liquid rock. They simply won't do it. Okay. So, and then love waves and Rayleigh waves are surface waves. So, let's think about this a little bit. We can use those P waves and S waves in a number of ways, but right now, let's think about the interior of the Earth. As I sip my coffee. Okay, so the Earth's interior, we have a solid crust that will not flow. We have a solid mantle that will flow. We talked about that with plate tectonics. You have a liquid outer core, a liquid outer core and a solid inner core, right? The Earth is about 8,000 miles across. That means it's about 4,000 miles from the crust to the center. So, how do we know that, right? How do we know that? Well, maybe, I don't know. Maybe we've drilled it, right? Maybe we drilled it. That's the deepest borehole on the planet. I know it doesn't look like much, but that is the deepest borehole on the planet. It was part of a drilling program in Russia. It's the Cullen number 6 borehole. There it is, and I could go to Google Earth and show you where it is in Russia. It's in northernmost Russia, up by the Scandinavian countries, but it doesn't look like much, okay? But that is the deepest hole ever that we have drilled. And so let's go back here and let's drill it, right? Let's add the Cullen number 6 borehole to our drawing, and let's drill. Let's by golly, let's drill it. Yeah, that's way too deep. that is way too deep. No, right? No. So that's not the Cullen number 6 borehole. That is right. And if you're wondering what I'm talking about, see that little tiny red bit right there? That's as deep as we've drilled. A few thousand feet. That's it. That's it. Okay. So yeah, not even into the mantle. Okay. Drilling is hard. I mean, drilling is hard. Let me go back here real quick and just show you something. So you've got to drill bit on one end, and then what you do is you have these pipes, and you thread those pipes into each other and use those pipes to turn the drill bit. Well, by the time you get, literally thousands of feet of pipe turning a bit, that pipe starts to chatter around in that hole. It starts to bind up. You run into all kinds of problems. The deeper you go, the harder it is. I've drilled, and it's a pain. It is a pain. And you can see here, there's literally rock caked onto this tricone drill bit. And so yeah, drilling is not easy. Drilling is not easy at all. But then so we're left with this whole problem though, right? If we haven't drilled it, what have we done? How do we know all this stuff, right? Well, hold on. No, I'm not dying. Okay, so let's say that rather than drilling there, let's say there was an earthquake there, like my little earthquake explosion thing. I'm very happy with that. But anyway, there's an earthquake there. Well, earthquakes make waves. As these waves travel through the earth, they do so kind of along a curve. They kind of travel like that, right? And so, but they travel all through the earth, not just along that one specific path, but all through the earth. And so let's take a look, right? So there's two paths of like an infinite number of paths between here and going this way, right? But notice this path stayed in solid rock, right? It stayed in, the crust and the mantle, both of which are solid, right? So there, you're going to get P waves and you're going to get S waves, okay? Notice here, though, this path nips that outer core, right? That outer core is liquid. It's going to absorb those S waves, right? And so over here, you're only going to get P waves. And so right away, with enough earthquakes in enough different places and enough different seismograms or seismographs, and we've got a bunch of them, you can work it out, right? You can absolutely work it out. And in fact, that's what we're doing right now on Mars, right? With the Mars InSight lander, right? This is a seismograph, right? It would be nice to have more, but we only have one. That's fine. That'll do for now. And so that is how we are studying the interior of Mars, right? Is by watching how seismic waves propagate. Now, in this case, we got to wait for impacts, right? Because that's how you're gonna make a Mars quake. Mars doesn't have plate tectonics, but there's enough impacts. They've got good data. In fact, the first round of papers is out right now. I need to be reading them, but I'm too busy writing and recording lectures. So anyway, so yeah, that's why we do it that way. And so look, it's not as simple as my silly little diagram, right? I mean, there's the you get a big earthquake and all kinds of things happen down there. All kinds of things happen down there, but we can use what's happening down there to figure out what's down there, figure out what's going on. One of the big applications of seismology is just that, working out what's happening in the interior of rocky bodies like the Earth or the Moon, right? There's a reason all those Apollo landings on the Moon left behind seismographs. That's how we study the interior, right? Same thing with Mars. So yeah. Okay, so we can use the difference, that time lag between P waves and S waves, to figure out not only how far away an earthquake epicenter is, but where an earthquake is, right? And so remember, so P waves travel faster, right? So if I have a seismograph shown here, right, the P waves will be the first to be recorded, right? So we need an instrument. The instrument that records earthquakes is called a seismograph. Now, we don't literally have cylinders with rotating pieces of paper and arms and strings and weights, okay? No. Okay. But this is the the principle that an inertial seismograph is based on, right? If I bolt this platform to the rock, if the rock shakes, right, that will shake the little rolling cylinder thinger. The pin on the weight, though, will not shake, and it will literally draw the earthquake waves on that piece of paper, and so you have a record of that piece of paper. We don't have we have fancy digital seismographs now, right? That you can just throw them down a hole and they'll do their thing, okay? And then we can report out directly to earthquake centers, and so our seismic networks now are much more sophisticated. But basically, they're inertial seismograms, right? That's just kind of what they are. And so, or inertial seismographs. I'm sorry. I'm going to cop to this right now. The instrument that records an earthquake is called a seismogram. No, I got that wrong. See, the instrument that records an earthquake is called a seismograph. The readout from a seismograph shown here. Now, see, I got it wrong again. No, I didn't. The readout from The readout from a seismograph is called a seismogram. The reason that confuses me so much is that is exactly the opposite of what I think it should be, right? This looks to me like a graph of an earthquake. Right? But it's not a seismograph, it's a seismogram. Expect me to make this mistake several times in the next few minutes. So, the readout from a seismogram, as you can see here, is called see, I just did it. The readout from a seismograph is called a seismogram. Okay, and I swear, if I was king of the world, that is the first thing I would change. But anyway, looks like this. Looks like this, right? And so now this is a real one. So the data, when the data are real, it looks all messy. But there's the first P wave right there. See my pointer? There's the first P wave right there. There's the first S wave right there. And then here are the surface waves strung out behind it, right? First P wave there, first S wave there. Time along this axis, okay? And so if this was January of 1994 or 85 to 89, I don't know what earthquake this is, maybe Northridge. But anyway, but you can see time along this axis here. Okay, and so yeah, let's look at it. Let's look at a cartoon one. Okay, so once again, time along this axis, right? First P wave hits here. First S wave hits here. Okay, surface waves back here. Okay, P waves travel faster. They're going to hit first. Okay, and so in this case, there is if this is 1 minute, there is a 1, 2, 3, 4. What was it? Hold on, I go to the middle. So 1, 2, 3, 4. About a 5-minute difference between that first P wave and that first S wave. Okay, here's the trick, guys. The longer that time is, the further you are from the earthquake, right? If you were very, very near the earthquake, the P waves and the S waves would not have time to separate out. So you would get hit with a P wave, and then, 10 seconds later, you get hit with an S wave. Okay. If, on the other hand, there's a much longer time between the P wave and the S wave, that means that you are further from that earthquake. They've had the time to spread out, right? Imagine there's no traffic on Highway 19, right? And so you got two cars. Now P waves are about 1.7 times faster than S waves. Let's say two. Let's say it's twice as fast, right? And so you light out in two cars, right? And one's traveling faster than the other one, right? You drive from St. Petersburg to, let's say, Weeki Wachee, okay, that faster car is going to be so far ahead of the slower one. If, on the other hand, you go, by the time they get to Tallahassee, there's a lot more distance in between them, right? If one car is traveling faster than the other, the longer they go for, or better yet, the further they are from where they started, the further ahead that faster car is going to be. It's the same thing with earthquake waves, right? The further you are from where that earthquake started, the further ahead that P wave is going to be, right? And so, yeah, now we can take this one step further. We can actually use a little graph. I mean, we could do the math, but let's use a graph. It's a lot easier, right? To figure out um, how far you are from the epicenter, right? And so, if your P wave and S wave time is, let's say, 60 seconds, right? Um, if they're 60 seconds apart, then if I follow that 60-second line over this way, I come down and it tells me I'm 580 kilometers from the epicenter, right? If it was 40 seconds, I would come over and I would come down and I'm about 390 kilometers from the epicenter, right? And so we can work out, not just, well, we're closer or we're further, but we can actually work out, exactly how far things are from the epicenter. And so, yeah. Okay, so sorry, I had to actually stop recording for a moment to get something else set up. But how do we get from this is how far you are from the earthquake to where is the earthquake, right? Because if I tell you, well, if you ask me, where do you live? And I say, oh, about 5 miles away, well, that's helpful, but that's not where I live. There's like a circle around where we're standing with a radius of 5 miles. That could be, I could live anywhere along that circle. So how do we work this out? Well, what you need is you need 3 seismograms. Okay, so let's take a look. Okay, so here I've got a size. There's a seismogram, right? The little lousy little one that I drew myself, but you can see. Let me get my pointers going here. So here's the P wave here, first P wave here. Here's the first S wave here. And here's a time in between them. It doesn't matter what it is. We call it delta T. Don't be freaked out by Greek letters. Delta just means the difference in, right? So it's the difference in the arrival time of that P wave and the arrival time of that S wave. Remember that time is kind of running along here. So let's look at a second one. So here's a second seismogram from the same earthquake, right? But this one is closer, right? You can see that, right? Two things. First of all, delta T is shorter, right? There's not as much time. If, let's just say this is 10 seconds, this is 5, right? So that delta T is smaller, so you're closer to the epicenter, right? Also, the waves get bigger, right? My little lousy little hand-drawn waves here are bigger, right? So let's look at a third one, right? And so here the delta T is even shorter. We're even closer to the epicenter now, right? The waves are really big, and yeah, so all three of these are measuring the same earthquake, right? So once again, the closer together your P waves and your S waves are, the closer you are to the earthquake. Okay, so we can do, remember this. Remember this graph right here. Okay, we can do a sort of a version of that. I'm going to just do a version of that on here, right, where I say, okay, look, here's my first delta T. Whatever it is, doesn't matter. We're not using numbers here. We'll go over to the line like we did on that graph. We'll come down, and that'll give us a distance, right? And then here, I come over, I come down. That'll give us a distance. That little d should be green. I forgot to change the color, by the way. Oh well. This delta t, come over, come down, that gives us a distance, right? And so now for each of these 3 seismic stations, I know how far they each are from the epicenter. Well, if I have a map, I can draw circles on it, right? And so for station 1, which should be green, I'm having color issues though, that's okay. For station 1, right, it's that far from the epicenter, whatever that number is, draw a circle around it, and there the earthquake is somewhere around that circle, right? Then we go to station 2, which is that far from the epicenter, draw my line, draw a circle, right? It crosses station 1 there and there. That's awesome. So if the earthquake is this far from station 1 and this far from station 2, it's either there or it's there, right? One of those two places, because that's where those two cross. So we need our third station, the one that's closest, right? You could do this in any order. But anyway, third station, that far from the epicenter, draw your line, draw your circle. It crosses there, and there's the epicenter, right there, right? Right there where those 3 circles cross, right? And so that's how you figure out, where the earthquake is, right? You take at least now, and you need at least 3 stations. In reality, you have hundreds of them. Okay, but this will work with hundreds of them too. All those circles should cross in that same place. Okay, and in the lab we're going to do, you're going to get a chance to do that. The computer is going to do the mapping and the hard stuff for you, but you'll get a chance to do that. So so if you want to figure out where the location of an earthquake epicenter is, right, use that delta t, that lag time between P and S waves, to determine how far 3 seismographs are from the epicenter, right? On a map, draw 3 circles around those 3 seismographs with radii that correspond to the distance from the epicenter. Where they cross, that's the epicenter, right? And here's another version of that too, right? I've got 3 seismographs, 3 different distances. Where they cross, that's the epicenter. Okay. All right. Doesn't need to be that close, guys. You can be pretty dang far away, and you can still, work this out. I mean, here's one that's 6,700 kilometers from Paris, 484 from Montreal, 5,500 from Sao Paulo, and those 3 circles cross right there in the middle of the Atlantic Ocean, where you can definitely get an earthquake from a convergent plate boundary there. So a really good, really sensitive seismograph can detect earthquakes from literally thousands of miles away. And so, you can do a lot of really, really good work with that. So, once there's an earthquake, your next question kind of is always how big is it, right? How big is the earthquake? Well, there's a couple different ways to measure that. The way that you're probably used to is something called the Richter scale, which we'll talk about here in just a moment. But another way that we do this is something called the Mercalli scale. Um, and the Mercalli scale is based on damage and shaking. And so here's the trick, right? As you get closer to the epicenter, that Mercalli number is going to go up, right? Richter numbers don't go up. If it's a magnitude 5 on the Richter scale or the moment magnitude scale, which is what we actually use, nobody actually uses Richter anymore. But anyway, if it's a magnitude 5, it's a 5 everywhere. Mercalli's not like that. As you get closer to the earthquake, Mercalli goes up, right? And so you can see here that, for example, a Mercalli 4 felt indoors by many, outdoors by only a few people, during the day, at night, some are awakened, etc., etc. And then, a Mercalli 5 felt by nearly everyone, many awakened. A Mercalli 6 felt by all, many frightened, heavy furniture moved, etc., etc. And you can see how, it gets worse and worse, right? By the time you're up here at a 10, well-built wooden structures destroyed, most masonry destroyed, destruction, destruction, destruction. And so, yeah. So once again, as you get closer to the epicenter, this number is going to go up. Okay, but look here. Look at a Mercalli. What is that? VII. That's a 7, right? Damage negligible in buildings of good design and construction, right? A Mercalli 8 is slight in specially designed structures, considerable in ordinary substantial buildings. And so suddenly, those are very qualitative descriptions, right? Those are very, that depends on what your idea about negligible and considerable and slight means, right? And so, and people can disagree on that. And so, the Mercalli scale is qualitative. Um, it can be, two equally qualified people can have an entirely different opinion about what the Mercalli number is, and so it can be kind of a little bit tricky. What the survey does, what the United States Geological Survey does, though, is they make shake maps. This is a shake map for the Northridge earthquake. So I don't quite have this set up, but we can set it up pretty quickly. Let's go to usgs.gov. And so this is the survey's website. Here's a magnitude. So this is kind of interesting. We had a magnitude 6.5 in central Idaho on the 31st, which is just yesterday, which is kind of an interesting thing. Not terribly unusual, but kind of interesting. And so let's see if we can do something here. So there we go. So we've got a shake map for this one, and you see here where it says, "Did you feel it?" And so, did you feel it? Felt report. Tell us. So let's say we felt this earthquake, right? And so here we go. Did you feel it? Let's say we did, right? And so then you take the little survey. Where were you during the earthquake? Let's say I was in a stopped vehicle. Let's say I woke up. Did others nearby feel it? No, well, no, most felt it. I'm not going to submit this, obviously, but the shaking was strong. How did you react? I was excited. How did I respond? I ran outside because that's just what I do. Was it difficult to stand? Oh yeah. And then you get it: swinging doors, creaking sounds, rattling objects, pictures moving, etc., etc. Right? Damage, right? Any additional comments? If you want to put your contact information, that's awesome, right? Then you hit submit. We'd have to finish filling it out somewhere. There it is. You hit submit, and then from that they make a shake map. There's a shake map for this one. Kind of sporadic, but there it is. Let's go back to my PowerPoint because I have a much better shake map. And this is the shake map from the Northridge earthquake. And you can see that this was a pretty big earthquake. And you can see that, here around the epicenter where the star is was, the most shaking. But notice also that it's not exactly a bullseye, right? The shaking kind of went up to the north, right? The worst of the shaking kind of went up to the north. And so if you're an emergency manager, you want to deploy most of your resources to the north of this epicenter, not in a bullseye around it, right? You go down here to the south of it, meh, not as bad as up here around Santa Clarita, let's say. So these shake maps are really very, very useful. So yeah, so we use Mercalli, but not as much, right? What you are definitely used to is the Richter scale or the moment magnitude scale. They're honestly not the same thing, not really, but for our purposes, they're okay, right? And so they're basically the same thing. The math is a little bit different. And so yeah, so here's the godforsaken formula that you plug into to get a magnitude. So what you do is you take the size of the largest S wave right there on a seismograph measured in millimeters. Okay, seismogram. See, I did it. Measured in millimeters, and then delta t, that travel time difference in seconds. You plug those two numbers into that formula, take a couple logarithms, multiply it by 3, multiply it by 8, no, 3 times the log, etc., etc. Subtract 2.92, and you'll get a number. Generally a number between, let's say, 1 and 10. Okay, Richter magnitudes can be anything from negative numbers. I mean, there is no real top or bottom of the scale, but effectively between 1 and 10. That's why you subtract 2.92 at the end, by the way. That puts the numbers in that range between 1 and 10. Here's the thing about the Richter scale, though, and the moment magnitude scale. It's not like, um, you know, a 4 is twice as bad as a 2. It does not work that way. Okay, every whole number you go up on the Richter scale releases 32 times more energy. So if there's two places, but if there's two places between, let's say a 2 and a 4, I've got my calculator out here, and it just, my phone locked up, and so here we go. So 32 and yeah. So no, don't do that. Here we go. A 4 is about 1,000 times worse than a 2 in terms of energy released, right? And so, as you go up on the Richter scale, the amount of energy released becomes phenomenal. By the time you're ups and eights and nines, you're releasing millions of times more energy than like a little magnitude 3 or a 4. Okay, a 4 is about the smallest earthquake that anyone's going to feel. And my kind of simple way of keeping track of this is a 4 you're going to feel, but it's not going to do any damage. A 5 you're going to do some damage, but you're probably not going to get anything collapsing. A 6, buildings are going to collapse, people are going to die. A 7, lots of people are going to die. An 8, cities are going to be leveled. A 9, you're going to start leveling regions. And the good news is there's never been a 10. So, the moment magnitude of the Richter scale goes from not very bad at all to really bad, really, really fast. And so you kind of want to keep that in mind as you think about that. And you can see here, a 4 to a 4.9 is light, felt by most people. 3 to a 3.9 often, but not always felt. And then, by the time you get to 5, we're doing damage. Now we're collapsing things. Now we're really killing people. Here we're killing a whole bunch of people. And the good news is there's a whole bunch of these per year, but not a lot of these per year at all. The other thing to keep in mind about Richter versus Mercalli is Richter doesn't change, right? You calculate that Richter magnitude, and that's what it is. Don't really need that. The good news is you don't actually have to plug into this godforsaken formula down here to get Richter magnitude. You can use something called a nomogram. And this is kind of what you're going to be using in the lab that I'm going to have you guys do. Only you don't have to actually use it. The computer's going to do it for you, but all you have to do is read off of it. And so remember that for Richter magnitude or moment magnitude, you need two things. You need the difference in arrival time between your P wave and your S wave measured in seconds. In this case, it's 24. And then you need to know the amplitude of your largest S wave, right? How big was that largest S wave? In this case, it's 23. I just literally measured it. Okay, so now if I come down here, I have something called a nomogram. And a nomogram is a graphic way to do a calculation, right? We've kind of been doing nomograms, right? When I say, look, go over to the line and down, right? Or go up to the line and over, right? That's kind of using a nomogram, right? We're not doing math, we're using a graph, okay? Well, this is the same way, only what you do now, you got three lines. You got a line for amplitude, you got a line for magnitude, and then you've got a line for the distance from the epicenter measured. Either you can measure in kilometers or that seconds, right? You know, the further you are from the epicenter, the more time there's going to be between that P wave and S wave, right? We're going to do it in seconds. So what you do is the magnitude is what you want to know, right? So if I lay a straight edge, the one end of it over here on the amplitude, in this case, the amplitude is 23 millimeters, so that's at 23. And then I lay the other end of the straight edge over here at the travel time difference, and that's 24, so 20, 30, so 24 is right about there, right? That line will cross that center line there at the Richter magnitude, in this case 5. And so if I have an earthquake that has a 24-second difference between P and S wave and an amplitude of 23 millimeters, its magnitude is 5, right? And so you can do that. Now, remember, I won't go back because I won't, but remember my 3 seismograms? See, I did it again. Those 3 seismograms that I had, okay? Each of those will give you the same Richter magnitude. They will all give you the same Richter magnitude, because what will happen is, you know, they'll get further away and the amplitude will go down, okay? So they'll get further away, but the amplitude will go down. That line is going to also cross at 5, right? Or they'll get closer, so this number will go down, but the amplitude will go up, right? So if you get closer, the amplitude goes up, you're still going to cross there, right? So if I had 3 different seismographs, they would all cross seismograms. They would all cross at that same magnitude. Every instrument measuring that earthquake will give you the same Richter magnitude, and we'll see that here in a moment. I just want to mention one earthquake here in the United States, and that was the New Madrid earthquake. This was the largest earthquake that ever hit North America, and it happened in 1812 in New Madrid, Missouri. Right? If you ask people where was the strongest earthquake to ever hit, you know, the United States, people will say, California, 1912. What? Yeah, no, 1906. No. New Madrid. 5 magnitude 8 earthquakes between December 16th, 1811 and February of 1812, and several hundred aftershocks. This was a huge event. The good news is not very many people died, because let's face it, how many people were living in New Madrid, Missouri in 1811? You know, not that many, and they certainly weren't living in big skyscrapers that would collapse or something like that, right? It was an absolutely huge earthquake. The fun thing about the New Madrid earthquake, though, is their fault is still active. It's still going on. Let me pull up. Oh, let's pull up Google Earth real quick and have a look at it. So let me go up here. Let me kick in my earthquakes, and we can come. Has there been any? Oh yeah, there have. Looky there. Okay, so yeah. So here's the New Madrid fault right here. Let me get rid of borders and labels so it's not quite so messy. Here's the New Madrid fault running right here, right along the Mississippi River. Now these aren't very big at all. That's a little magnitude 2.2. It's about 7 kilometers, 4.5 miles down or so. Not very big at all. But look, there is still seismic activity happening here along the New Madrid fault zone. And so yeah, so let's ask ourselves why real quick, because look at North America. right? We have a lot of earthquakes that are nowhere near. I mean, look at these down here happening right now in Texas. Look at this. Look at all this, right? We're getting. I mean, there's a little. I mean, we're getting some pretty good earthquakes, but they're nowhere near a plate boundary. Here's one that this is probably the one that happened. Let me put my belt borders right in just real quick so I know where I am. Yeah, Idaho. Yeah. So this is the one that happened in Idaho just the other day, and you can see the aftershocks. And so there's a magnitude 6.5. That's a pretty big earthquake. I mean, a magnitude 6.5 in downtown San Francisco, and you'd be talking about a lot of dead people. And then you can see all the aftershocks. And so, but that doesn't seem to be anywhere near a plate boundary, right? And so, here's the trick. And I could go all over the world and show you, but I'm not going to. North America in general has a lot of earthquakes that are nowhere near a plate boundary. These in Oklahoma are due to petroleum exploration and hydraulic fracturing, by the way. But we have a lot of earthquakes that are nowhere near a plate boundary. These are called intraplate, or they're also called it's easier to say inboard earthquakes, right? Lots of earthquakes nowhere near a plate. Right? No one else really has this. No one else really has this. Australia doesn't, Europe doesn't, Africa doesn't. I mean, I could go around the world and show you, but just trust me, they don't. So why do we get so lucky? Well, we're being squeezed. You've got a divergent boundary, over here, shoving North America this way, and there's nothing over here to relieve it. It's just shoving it up against the San Andreas Fault. And so North America is being squeezed. And so if there is any weak rock anywhere in North America, it's going to break and it's going to slide. And so we get a lot of these inboard earthquakes. There is weak rock right here along the Mississippi River. The Mississippi River is where it is because when Pangea tried to break apart, it tried to break apart there. And so Pangea is like, hey, here we go. I'm going to break. Y'all hold on. And it starts to break here. And then it goes, you know what? Never mind. I'm going to break over here instead along what is now the East Coast. But there was some uncertainty on the part of the supercontinent about where it was going to break. And it started to break here. That's why the Mississippi River is where it is. And so if I come back to my PowerPoint, you can see this drawing here showing this buried rift. Let me do my pin again. I missed my pin. Okay, so showing this, this buried rift here, right? That's where Pangea tried to break apart. You can see there's ancient faults out there. There's bodies of magma that were brought up. And so you got a lot of weak rock up and down through here. Y'all can't see me pointing, so let me go back to this. And so we got a lot of weak rock up in here, and so that regional compression set up by the mid-ocean, the Atlantic mid-ocean ridge over here pushing this way, and nothing over here to relieve that pressure, so it gets pushed back, and weak rock plus regional pressure equals earthquake. So we get a lot of earthquakes. Another hazard, though, associated with earthquakes is tsunamis, or quote-unquote tidal waves. Now, these don't have anything to do with tides, I know, okay? But if I say the word tidal wave, it at least mostly puts the right image in your mind, okay? So, these can be caused by a lot of different things. Earthquakes, volcanoes can definitely cause local tsunamis. Landslides can cause local tsunamis. Meteor impact can also cause tsunamis. But really, earthquakes, right? That's the thing, right? And I said local just a minute ago. That was wrong. They can cause global tsunamis. So what's going on here, right? Well, most tsunamis happen in the Pacific Ocean. Okay, that's where most of them are going to happen because the Pacific Ocean is surrounded by the tectonic setting that gives us tsunamis. Here's the trick with a tsunami. It's not the shaking. Okay, the shaking is not coherent enough to make an earthquake. What has to happen, and I'm going to show you on this diagram, what has to happen is this plate goes underneath that one. This plate bends downward. And then when it gives, this is the head wall, it bounds upward into the water, right? And so imagine putting your hand on the bottom of an aquarium and going up and moving your hand up, right? That's what you're going to get here, right? You're going to get rock being displaced upward into the water, right? There is a cliff off the coast of Japan that was not there before 2011. Right, and so and that sudden shoving of that rock upward, that's what makes the tsunami. So it's not the shaking, right? And so if you want to warn people about a tsunami, it's not enough to say, hey, there was an earthquake, get off the beach. Right, you do that about the fourth time you do that, and people don't get off the beach because they just don't believe you. So what you have to do is actually sense the wave. And so what a tsunami warning system consists of is a pressure transducer here on the bottom that when that wave goes over, it'll pop that thing and it'll go, hey, 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 hey. Yeah, there's a wave there, a big one, right? Little ones won't reach all the way down to the bottom. The big tsunamis will. And so pops that pressure sensor. That pressure sensor talks to the buoy talks to the GOES satellite talks to the emergency management center, and within seconds you know and you can start warning people. Here's an actual photograph of one. And so then you get people off the beach, right? Not just because there's an earthquake, because, right, evacuation fatigue is a thing, right? People don't like being just told to go run away every time some little thing happens, and after a while they'll stop. So it is a thing. I want to show you a video of the tsunami. I'm a grainy picture again, and it wasn't grainy to start with, I swear. Anyway, show you a video of the tsunami in Japan in 2001. This was an unprecedented event. I believe it was a magnitude 9.7 or 9.8 earthquake, right? Offshore, set off a tsunami. So after, everything shakes to the ground, suddenly there's this huge wave. Japan is as well prepared for a tsunami as you can reasonably expect anyone to be. They truly are. And so, what you're seeing here is the tsunami flowing over the tsunami protection wall. Okay, so I'm going to turn my Bluetooth off here. Let me do that. Hey guys, so check it out. Sometimes when you put a YouTube video in your YouTube video, that triggers a copyright claim and they block it. The tsunami video I wanted to show you is apparently one of those videos. So I'm going to put a link to it. You can watch it on your own. And now we're just going to go ahead and move on to the lab. Okay, so coming up next will be me explaining how to do the lab. Alrighty guys, thank you very much. Bye-bye. At the lab exercise. And so I went ahead and unlocked it for whatever section this is. And so it's called Virtual Earthquake, and it is a totally online thing. Okay, so if I click on Virtual Earthquake, it'll bring it up. It's up here. There's some directions from me. Please don't mail me a certificate. That just clogs up my email. Oh my gosh, especially not now, guys. I'm getting so many emails from so many people. Not just you guys. You guys are great. You guys are fine. But like I've got publishers mailing me with, here, let's put your classes online. And I've got administrators emailing me and all just all kinds of stuff. So please don't add to my, I mean, if you guys have an issue, email me. Definitely. But please don't email me your certificate because that's going to be a thing. So anyway, you'll see what I mean by certificate here in a minute. So there's a link to the exercise. Okay. Words. Words are good. Read the words. Please read the words. The words are good. What are seismic waves? Here's a seismogram showing you what I've been telling you. First P wave here, first S wave here, amplitude, SP interval, that delta T we've been talking about, etc., right? Read the words. They're very good words. Read the words. Okay, then pick an earthquake. All right, you've got Mexico, Japan, Southern California, San Francisco. I'm going to do San Francisco, and because I'm going to show you how to do it. Okay, so first thing, determine the earthquake epicenter. Okay, so here's the region we selected. Remember, here's some words, right? Measuring the SP interval, so the time from here to here, from here to here, so you can see me pointing. And so once again, words are good. Read the words. I've got degrees in this stuff. I don't need to read the words. I've already read plenty of words. Okay, so view seismograms. Here we go. So they show you the seismograms. Now, what you might want to do Ooh, don't do that. What you might want to do though is up the magnification on your computer screen. Okay, it'll make it easier to see what's going on. And so the handy thing here is that they start the clock when that first P wave hits. So when you're first of all reading that SP interval, all you have to do is read off when that first S wave hits. That's it. Okay, you don't have to do any subtraction. You just have to read off this number. Okay, so first P wave hits here, first S wave hits there. Now, you want to be as precise as possible when you're doing this, which is, like I said, while you might want to up the magnification on your computer screen, you can see I'm at 240% right now. So if I look at this, this is seconds along the bottom here. So 40, 42, 44, 46, 48, 50. So each of those blue lines is 2. So if I look here, I'm not quite at 50. I'm not quite at 48. Maybe let's try 49. 50 would probably do, but let's go with 49. You want to be as precise as possible because if you're not, it's not going to work. And they're going to tell you, hey, that didn't work. Go back and do it again. Okay. If I look here, there's the first P wave. Here's the first S wave, and it's right at 72, right? It's right at that little blue line. That's 70, that's 72. So let's go with 72. And then, okay, so here's the next one, right? First P wave there, S waves here, so that's 60, 62, right at about 64. So let's go with 64. 64. Okay, now what we need to do is we need to convert that SP interval into distances, right? We're going to use that graph. In fact, this exercise is where I got the graph. So words, read the words, and then here's the graph. Okay, so let's zoom out. We don't need to be quite this zoomed in now. There we go. So they brought over your SP intervals, so now you just want to use those to get to kilometers. So what we want to do is we want to go from time up here to distance down here, right? So 49 seconds. Well, if I look at this, 40, if that's 45, 46, 47, 48, 49, 50, right? So each of those is 1, right? So 49 is going to be that blue line right below 50, right? 49. I go over to the diagonal line, and then I go straight down, right? And so I tick off right here. That blue line right there is about 480, right? 400, 420, 440, 460, 480. It's about 480 kilometers. So I come over here. I type in 480. Elko, Nevada is my other station at 72 seconds. That's what I got off of my seismogram. So 72 seconds. I'm very proud of myself for saying seismogram and not seismograph. So remember, on this axis, each of those blue is 1. So 72 is right there, right? So now I take 72 over to the diagonal line and then down, and it's basically right on 700. So we can probably get away with 700. Vegas, 64. 65 is here. 64 is one blue line below it. If I come over, and more or less at that blue line, maybe a little over, and I come down, that's about 620, right? Remember on the x-axis, each of those blue lines is 20. So let's go with 620. So my epicenter is 480 kilometers from Eureka, California, 700 kilometers from Elko, Nevada, and about 620 kilometers from Vegas. Let's find the epicenter. Click on Find the Epicenter. Excellent work. Hooray. It's almost as if I've done this before, y'all. So, yeah. So you can see the map. So what they've done is they drew a blue line around Eureka. Okay, they drew a green line around Vegas, and they drew a yellow line around Elko, Nevada, and they all crossed right there, just south of San Francisco, near a little town called Loma Prieta, actually. So, I happen to know that. Okay, so now what we're going to do is we're going to calculate the Richter magnitude. Okay, so click the next one. Okay, so here we go. Richter magnitude explained, everything you want to know about Richter, okay? And what we need to know We already know the SP interval. That's the first thing we did. So now all we need to know is the size of the largest S wave, right? And they show you that here. Go to the next page. Okay, the Richter nomogram. So now they explain this nomogram, right? This graphic way that we are going to calculate the Richter magnitude. We're not going to have to go in and, do any math. Okay, so go to the next page. So we need to know the size of the largest S wave. So look, assume it's up. All right, intuitively we all want to go up and assume it's up. Okay, you don't need to go, well, is this one bigger or is that one bigger? Go with the biggest one up. You're fine. Okay, so if that's 200, that's 250. So that means that's 210, 220, 230, 240, 250, right? So each of those is 10. So if I look here, 250, 260, 270, 280, 290. It's kind of between 280 and 290. Let's go with 285. 285. Okay, then look at this one. And 50, and one blue line above that is 60, so that one's about 60. 60. Okay, and then I come down here, and once again, my roller's not working very well. There we go. And so that one's right at 100, right? That largest S wave is right at 100. 100. Okay, so submit to nomogram. So this is how this is self-correcting, right? If you were wrong about your amplitudes, all those aren't going to cross at the same place. Remember when I showed you that nomogram, I said all three of those seismographs will give you the same Richter magnitude, right? And you can see here that they do, right? The ones that are further from the epicenter have lower magnitudes. The ones that are closer have larger magnitudes. They all cross the same point right there, which is about 7. But that's 7.5. That's about 7.1, right? So let's put in 7.1, 7.1, and let's confirm the magnitude. And hooray, we're done. Okay, so now put my name, my institution, SPC, SPC, your city and state, who knows anymore? Can't type. And okay, so do not email your instructor. Okay, so here's what you want to do: get your certificate, right? So get your certificate. There it is. Yay. Okay, so what we want to do is, you can either do a screen capture of that. You can do, I don't know, y'all. Oh, actually, right clicking. Actually, I know this. Right clicking and saving the image will absolutely save the image. Stick it, save it to wherever. Save the image, right, and then upload that to the Dropbox, right. Look over here. Virtual earthquake. Here we go. Right, and there's the Dropbox, right? And so just, right click, if you want to just right click and save it. I don't know what the Mac version of that is. I don't do Macs, but anyway, or iOS or whatever. But anyway, that'll work. And then just upload it to the Dropbox, right? I've had people take pictures of it with their phone. If you want to do that, if you're like, I don't know how to right click saving, I don't know how to do that, just take a picture of it. I don't care. Okay, just work out a way to get it into the Dropbox. Like I said, right click save image works really well. So that will absolutely work. Okay, alrighty. So there's earthquakes. Awesome. Okay, I got a cough. I'm not dying. I'm talking. Okay, so alrighty, there it is. And so you all take care. I will be back with geologic time probably tomorrow, because I really want to get this stuff done, because I got to start running that test. So I will be back with geologic time probably tomorrow, maybe the day after, but hopefully tomorrow. And then that'll be everything for the test. So there we are. Okay, talk to y'all later. Bye bye.